everyone, welcome back to the latest lecture session. Very quick recap of what we discussed in the previous session. We were talking about sedimentation in the context of removing the suspended particles in the wastewater, or for that matter water, let us say. And why are we doing that? Obviously because it is easier to do, right? If not, you are going to have issues down the line, and also if you remove some organic content right now, it is cheaper than providing oxygen and trying to remove the organics later, let us say. But here the stress is not on removing organic contents per se, the stress is on removing, or the goal is to remove the suspended matter, and during that removal some of the organic content or the BOD will also be removed, right. In that context we saw that there were four types of sedimentations or settling, type 1, 2, 3 and 4. The first one is discrete, as in the particles do not interact, and in that context we saw that Stokes law is applicable for laminar flow conditions for spheres, right. And then we also looked at coefficient of drag and the relevant laminar conditions, turbulent conditions and so on and so forth. And then we looked at the critical variable, which is the surface overflow rate. In the context of both the upflow and the rectangular flow, we saw that, let us say now let us look at this particular upflow clarifier, let us see. So, upflow, my volume or the water is going up, particle wants to settle down. So, if this velocity is higher than this, the particle will move out along with the water. But if the settling velocity is higher than this particular water velocity, obviously the particle is going to settle down. In that context we came up with the surface overflow rate, and we also looked at the same aspect for our rectangular flow, not rectangular, pardon me, for the horizontal flow conditions. In the horizontal flow we saw that again V naught is the relevant threshold. If the settling velocity is greater than or equal to that, yes, we are going to have removal, but if it is what do we say, less than that, again it is not going to be 0% or such, it is going to be a fraction. Why? We assume that the particles are uniformly distributed. So, if the relevant particle comes in at the what do we say, certain height, it might be removed, just be removed, but the ones above it might not be removed, and we looked at that. So, let us look at it in relatively greater detail, as in what is the effect of depth on the removal ratio, let us see, right. So, what did we discuss earlier? So, we have this basin, and let us say this is the relevant V naught, and if Vs is equal to V naught, just equal to V naught, it will just be removed if it is coming at the topmost location. But if it is coming at the bottom location, obviously not bottom, less than the top, when Vs equal to V naught, obviously that particle will be removed. But what about the case when the Vs is, let us say, half of what do we say, V naught now, right? What is that going to be the case? So, in that context, let us say if the particle again is coming up at the top, so let us say it is going to get out here, let us say, right, get out here. So, it is not going to be removed, but if it is coming out at h by 2, then I guess you are going to have removal, yes. So, you are going to have fractional removal. So, let us look at this effect of depth on removal ratio. So, what we just discussed is what we have out here, let us say. Keep in mind that the flow rate is relatively constant. The horizontal flow rate is what do we say, not horizontal flow rate, horizontal velocity is constant, let us say. We are dealing with this what do we say, theoretical value of V naught, let us say, right. So, here we have relevant conditions V and V naught, and we can see which one will be removed or in which case it will not be removed, let us say, right. So, that is something we already just discussed in detail. So, let us look at this. If I decrease the relevant height, what is going to happen? Will it increase, decrease or not be affected? As you can see, and as we also saw from the relevant equation, we see that the tank depth does not increase or decrease the removal ratio, let us see, right, because again the flow rate is also going to what is it now, the flow rate is relevant or relatively the constant, let us see, right. Flow rate is constant though, even though if you decrease the height, it is not going to change your relevant efficiency of removal of the suspended solids, right, because what we are concerned about is just this V naught. So, if I decrease the height, the horizontal flow velocity will increase compared to this case, let us say, right. So, that is what we have, a particle which at h would be somewhere out here, I guess is now somewhere out here, let us say. Why is that? Because this horizontal flow velocity has increased
because you are decreasing the height. Again, reduced tank depth, as we can see, does not really affect it. But what can you do? You can provide a tray, an intermediate tray out here. How is that going to help? Let us say, right, half h and half h. That will help by increasing this surface area, right. As we saw, what is it now? V naught will be dependent upon, what is it? Q by surface area, AS. For rectangular basins, it is from the top view, we know that it is length into width, let us say, right. That is what we have. So, here by what is it, providing in the tray, we are effectively decreasing this V naught, if we may say so, right. So, you see that tray in the tank provides added floor area and thus leads to increased solids removal, right. So, that is something to keep in mind, right. So, we just looked at the effect of depth on removal ratio, fine. Let us just look at one example. So, two tanks in parallel, flow is coming in and we have two tanks in parallel, yes, and they are used for color removal, but looks like with alum coagulation, but we are not concerned with the coagulation flocculation part out here. We are only concerned with the sedimentation. I guess this example I should have used after type 2, but never mind, it is a general example. The combined flow rate is 0.3. So, through each it will be 0.15 meter cube per second, right, and the depth of the tank, each tank is 2 meters and each tank has a detention time of 1.5 hours. So, what is the surface area of the tank, right, and what is the overflow rate? Let us say that is going to be relevant to these particular variables. Well, pretty simple, what do we say, calculations. So, two tanks in parallel, so flow rate is half of the total. Q from meter cube, what do we say, convert Q to meter cube per hour for each tank. So, looks like it was given in seconds, but our time for detention was given in hours, right. So, if there are errors in the calculation, that is fine, you can just correct that yourself. And volume is, what is Q, is equal to volume per time. So, if I want to calculate volume, I need to multiply Q, the flow rate, with the relevant time and I get the relevant volume of the relevant tank, right. This is the volume for each tank because the flow rate that I have used is the flow rate through each tank, let us see. So, I have the relevant volume and now the depth is given. So, depth was given to be 2 meters. So, from that I can get the, so this is 2 meters, right, and the flow is going in this direction, right. This is the side view, right, but I need the surface area from the top. If I look at the top view, right, L into W is what I want, let us see, right. So, what is it that we have? That turns out to be 405 meters square, let us see. Now, once I calculate the surface area, I can calculate the overflow rate. It is pretty straightforward, Q by surface area, let us say, right, 540 by 405. So, looks like it is 1.33 meter per hour. So, that is just some algebra, but again this is not the design. We will look at the design in greater detail later, right. Again, Q and time was given. So, we calculated the volume, right, and we already had the depth. We calculated the relevant surface area and from the surface area we calculated the overflow rate, which gives us the relevant threshold, right. So, let us move on. So, type 2 settling. So, the type 1 settling, each particle settled independently. Type 2, you are going to have flocculation occurring. Flocculation, generally you can promote it by adding relevant what do we say, coagulate. If not to, you can observe it, but why is it that we are going to observe flocculation, or what are the driving forces? As discussed earlier, discrete settling, ideal case, very rarely in water and wastewater treatment, right. Why is that? Many particles have different sizes and properties, right. So, what do? They have different settling velocities. Let us say this one starts out here and this one is out here, but this is heavier, right, and let us say that is settling down at a faster rate. So, what is going to happen? And this one is what we say relatively less heavier and has a less settling velocity. What is going to happen? You are going to have this particular flocculation occurring. So, they collide with each other and agglomerate, right, and that leads to what we have, or what we are calling as type 2 settling or flocculation settling. So, flocks formed, again you have the relevant source here. Let me just point out some aspects here. As we mentioned in the biological process, you have certain kinds of bacteria forming, right, filamentaceous, right, and such, or flock forming and filamentaceous. So, you are going to have flocks being formed, again flock forming bacteria, and with the backbone being the filamentaceous bacteria. There has to be a balance between both. We will discuss that later. Why is that? If not, if everything is suspended and never settles down, I am going to have issues. So, after my aeration, I want these kinds of bacteria to be such that they form flocks. Now, they are bigger and then they settle down relatively fast. So, that is what we see here. What do we say? Initially, we see small weak flocks or pin flocks out here, which would not settle as fast. Again, small weak flocks, but with what is it now? A and C 100 bar zoomed in, right? That is what you see out here, B zoomed in. And then here we have flocks containing microorganisms and flocks containing filamentous microorganisms as the backbone, right. So, you have these two are at the same, what do we say, magnification, and these two are at a different magnification, let us see, similar but different from A and C, let us see. As you can see now, right, from B and D, the kind of flocks that you have, relatively bigger particles or bigger flocks, and again with the relevant filamentous microorganisms or filamentous bacteria, which form the backbone around which the flock forming bacteria, let us say, are going to agglomerate, and now you are going to have bigger particles and settling down. Again, different what do we say, not application, example of flocculation, let us say. So, causes, as I mentioned earlier, differences in settling velocity, right, and also you can also have, let us say, different pockets of water having different velocities itself. One is the particles being different, right, different densities and such, and colliding, or the particles, and also the velocity of water itself might be different, or you might have gradients in the velocity, let us say, right. So, that is what you are going to look at. And what are the benefits now? When two particles combine, typically I have a bigger particle, and then I am going to end up looking at faster settling or observing faster settling surge. And also, flocks that are relatively smaller first, as they settle down, they can get bigger. Why is it? Because they have a sweeping effect, and that is why these we see sweep flocculation, right. That is something to keep in mind. Faster particles tend to sweep. So, there is no good theory, that is one aspect to keep in mind. Why is that? Let us say if I am trying to design a sedimentation tank, a new sedimentation tank, and if I want to look at the relevant design and I just want to look at it or come up with the design by developing a model. Why is that difficult? Because unless you have the actual wastewater, it is difficult to mirror it, and also you do not know how the flocks are going to behave, because the relevant velocities are going to be different in your model and the actual tank. So, you are always going to have issues, but again for what do we say, looking at the performance of the current tank, or for what do we say, improving the size or upgrading the facilities, you can look at this column theory. So, first the diameter is large enough to avoid wall effects, typically 15 centimeter, height equal to depth of the proposed tank, right, whenever possible, or greater, typically it will be around 2 meters or 3 meters and such, and you are going to have sampling ports and such, let us say, and then percentage removal is plotted versus depth, let us say, right. And how am I going to plot it? Let us just see. Here I have the different depths at which this is my vessel or my model, let us say, and I have sampling ports at different depths, right, and I am going to calculate the percentage removal in this manner, Ct by C naught, concentration, what do we say, at time t, I guess, right, remaining at time t, and initial concentration, let us say, percentage removal will be 1 minus Ct by C naught into 100. So, what is it now? After 5 minutes, I will measure by taking a sample what is the percentage removal at 2 meters, at 1 meter, and at 0.5 meters. Obviously, at the shallower depths, let us say, you will see relatively clearer water, and here it is still settling, right. So, here situation at C naught is this, situation at C naught is this. After 5 minutes, what will you see? Relatively clearer at the top, right, but relatively less clearer, but with in the middle regions and here I guess, right. So, that is what I am trying to what do we say point out by drawing a relatively poor figure. So, we will see relatively greater removals even at shorter time periods at the shallower depths, but not as much removal at the deeper depths, let us say. So, obviously, with increasing time at the same depth, you see that the percentage removals, the measured values are given in the circles, they are going to increase, let us say, right. So, that is what you see out here, and obviously again with depth the percentage removal will decrease, right. Again at 2 meters with time you see that the percentage removal will increase, and here once we measure it, I can now come up with these particular curves which are more or less interpolated what we say based on interpolated data, as in I have this removal 41, 19 and such. So, for 30% removal I can interpolate and get the relevant curve, let us say, and this point of intersection with the bottom of my particular tank, let us say, will define the overflow rate, let us say, right. V naught will be equal to what now? H by T A, right. So, that is the relevant aspect, let us say. So, depending upon that you can calculate the relevant removal for that particular overflow rate V naught, let us say, for this particular detention time, right. So, again this is the detention time, and how do we get this line? This is based on your particular interpolated data. For this detention time I can calculate the overflow rate, right, and how is the what is the removal at that particular overflow rate, right. Overflow rate is given, and how do I get that? So, that is going to be RA. RA is already 30% for this particular case. Total removal at that particular TA, right. What is that equal to? RA, right, 30% plus what is this H1, right, H1 by H. H1 is nothing but the midpoint between these two particular points of intersection, right. H2 is nothing but the midpoint between this point and this point. You have this line out here at TA, and the midpoint between these two particular iso concentration lines will give you H2 and H3. RB is in this case the second one. What is the RB? I guess if that is 30, maybe this is around okay 40%, and RC is 50% and so on and so forth, right. So, you will be able to get that. Rather than what do we say just speaking out loud, let us look at the relevant data and see how to go about it. So, the following data were obtained to design a settling tank. Initial solids concentration was 20 milligram per liter, and we want to determine the detention time and the overflow rate such that we will get 60% removal of the suspended solids, right. So, we have to see how to go about it. So, let us look at the data first here. So, they measured the depth at 5 levels and times I guess time intervals at different time intervals, right. So, and then they gave us the data as in this is the suspended solid concentration at what do we say 0.5 depth after 10 minutes. Obviously, as you see the concentration decreases with time at the same depth, but increases at the same time with increasing depth, let us say, right. So, that is something we already discussed, and let us move on. So, percentage removals, I can calculate the percentage removal from that, because I know that the initial one is 20. For example, here it is 14, right, 20 minus 14 6, 6 by 20 into what do we say, let us say 100%, or in the other case it was 15. So, 5 by 20 into 100, right. So, 1 by 4 into 100, 25%. So, that is what we see. Thus, you can calculate the percentage removals at this particular sampling points and times, let us see. And what will that allow me to do? That can allow me to interpolate the data, and then let us see how we can get this. So, now I want these iso concentration lines for 20, 30, 40, 50, 65 and 70%, let us say, and at different times I will get this iso concentration lines by interpolating the data between these particular data points, let us see, right. Obviously, I am not going to go into interpolation right here, right. So, we will get this data. From this data I can plot these supposedly iso concentration lines. For example, let me just look at how we got this blue line. So, we see that at what is it 10 minutes, right, we will have 20% removal at depth of 2 meters. So, that is why we see at 10 minutes, right, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So, 10 minutes we will have 20% removal at depth of 2 meters, and then here we will have 30% removal after 10 minutes at a depth of 0.5, right. So, the next one is 30%, right, 30%, and we will have it at 0.5, right, and let us see what else, right, 30% removal, and more or less we will what do we say, plot this data in this fashion, right. So, let us move further. So, I plot all these iso concentration lines, and again they are more or less ranging from 20 to 80%, and we get this. So, as we mentioned, we will look at this point of intersection and draw a vertical line, right. And what is this point? This point will be the middle of the point of intersection of these 2 points. There are 2 iso concentration lines here. This is extrapolation, though we have the data only from here. We extrapolate and assume that it is going to intersect 2.5 out here, and then I am going to get this midpoint, let us say, right, this midpoint. Why do I need to get the midpoint? Because if we looked at the relevant equation out here, the percentage removal, we need to get this midpoint, right, and H1, H2, and so on and so forth, right. So, that is what is needed out here. So, from that, after I calculate that, what will I be able to do? I will be able to calculate the percentage removal, not calculate, plot the percentage removal and the detention time, let us say, right. And from this, what was the percentage removal that was requested? I believe it was 60%. Let us look at it, okay, 60% removal was required. So, what do we see? So, for 60% removal, from this graph I see this relevant detention time, maybe 53 minutes or so is required. And what is the overflow rate? I can either calculate that or again plot, look at the plot. So, for the 60% removal, if I calculate the overflow rate, I guess it comes out to be 70 meters per day, let us say, and the detention time is around 55. But again there will be some what do we say, values, because we need to look at factor of safety, or to when we design this. So, 1.75 and 0.65, but again we will provide that in the exam if we look at that, right. Again one aspect is you will have different levels of removal, and that is what you see out here. So, I am almost out of time for this session, and I will continue looking at, or we will continue looking at some of the relevant pictures that will give a clearer idea of what happens out there in the actual sedimentation basins, but that will have to wait until the next session. As usual, thanking you for your patience, I will end the session.